Hey, this is Mr. K, and today we're going to go over how to tell if a function is differentiable or not in a given spot. So typically with differentiability, there are 4 different cases where you have a function that is not differentiable. The first example is going to be a corner. Typical example of a corner is going to be the function f of x equals the absolute value of x. And if we look at a graph of that, you'll see that right here at x equals 0, that's where your corner exists, and that's where it would not be differentiable. A way to think about it is kind of like, a limit exists at 0 if the limit from the left and the limit from the right are equal. The same thing can be true about differentiability, which is the derivative, which is also known as the slope. Is that the slope on the left and the slope on the right need to match. If I look here, the slope on the left would be -1. The slope on the right would be +1. Because those two don't match, this would not be differentiable at x equals 0. A similar example is called a cusp, and an equation that has a cusp would be the equation x to the 2/3 power. A cusp looks very, very similar to a corner in that, and I know my picture's not like super great here, but only instead of like having a nice rigid corner, it kind of like curves in and then kind of curves back out. So that's an example of a cusp, and again, it would not be differentiable at x equals 0. However, it is differentiable on all the other x values, both positive and negative. It's just at this specific cusp or at the corner where it would not be differentiable. The third example is going to be a vertical tangent. And the typical example for a vertical tangent is going to be the function, the cube root of x, or x to the 1/3 power. And again, a graph of that would show we're approaching, and then all of a sudden, once we get to 0, there's going to be a vertical tangent right there, and then we curve back out. So right at this x equals 0, you're going to have a vertical slope there, so the graph will be going straight up and down. And that slope is undefined. So because that slope is undefined, our derivative is undefined, because our derivative is our slope. So it would not be differentiable at x equals 0. And then the last example is just a discontinuity. It doesn't matter what it is. Typically you'll see these in piecewise functions. So if I have like an equation like x squared minus 2, and then I'll say we'll have x plus 2. Right there at that jump discontinuity, that would be where it's not differentiable. So again, only did not differentiable, the derivative doesn't exist at x equals 0. It would exist at all of these other x values. And again, if you think about the slope here, the slope as I go from the left, let's actually use the equation here. So we had x squared minus 2. This will be x plus 2. If you were to use the derivative, a limit definition of a derivative, or if you know the shortcut, you could use the shortcut. The derivative at 0 for this equation would equal 0. So like the derivative on the left is going to be 0. The derivative on the right, so if you were to, again, use the limit definition of a derivative or the shortcut, you should get a derivative of 1. So the derivative on the left doesn't match the derivative on the right. So that's how I know it's not going to be differentiable at that spot. The only other thing I would say about differentiability is that if something is differentiable, so if the derivative does exist at that spot, it also implies that the function is continuous at that spot. So if it has a derivative, or if it's differentiable, it is automatically continuous. If it is continuous, that doesn't mean that it is differentiable. And a good example of that is our vertical tangent here, where this is continuous, but right at that x equals 0, where we have that vertical tangent, it would not be differentiable. So thank you so much. Have a great day.